There are a lot of patterns on the periodic table. In this goal, for this goal, you will want a periodic table that you can refer to. Also, in your packet, there is a page that has a blank periodic table that you can use to help you take notes. The periodic table has a lot of patterns, and so just to get you to start looking for patterns, I want you to solve this puzzle. So go ahead and pause the video and solve the puzzle. Okay, we're back now. So now on this puzzle, we see that it starts with 54, and then going down, it skips a space, and then we have 74. So we can conclude that 64 is right there. And we see that in the top row, it starts with 54 and ends in 59. And we can just count across to solve the puzzle. And we can do this for the next row. So 65, 66, 68, 69, and then we have 75, 76, 77, 78, and 79. So we're counting in ones this way, and on this puzzle, we're counting by tens. So that is the puzzle. Let's try another puzzle. Okay, this puzzle is a little bit different, but see if you can figure it out. Go ahead and pause the video and try to complete this puzzle. Okay, we're back now. So for this puzzle, we see that in this middle row, it seems that there's a 3 to begin with. So I'm going to go ahead and put a 3 all the way across. And so because of that pattern, I think it's going to be the same thing. Put a 4 all the way across. And working backwards, I got 2 all the way across. And then let's look and see what's in the square. So it looks like we have some like p's raised to a power. So, and I can see right here, there's a P1, and here there's a P2, and then later on over here, there's a P4. So I'm going to count like this: P1, P2, P3, P4, P5, P6. So I can fill in the whole puzzle this way. This is the pattern. So, and this is going to help us when we're looking for patterns on the periodic table. All right, so this is filled in. So, and this is very similar to a pattern that we see on the periodic table. So now that you practice some of your figuring out puzzle skills and looking for pattern skills, let's look at a periodic table and look at how it's arranged. So you do have a blank periodic table at the front of your packet that you can follow along with. So you should know the periodic table is arranged by the number of protons, but it is also arranged by the number of electrons. So if I had 5 protons, I would have 5 electrons. And it is, as scientists, we want to describe what each of those electrons are doing. And so each electron in an element's collection of electrons, it has an address. So the first thing you need to know is what sort of neighborhood it's in. So it's arranged according to blocks. So the first 2 rows on your periodic table, this is known as your S block. Then right next to the S block, we have the D block. And next to the D block, we have the P block. And down at the bottom, we have what's known as the F block. So these letters, they used to stand for something, but they do not stand for anything anymore. So here's F here. So the words have gone away, but the first letter of the word has stayed. So I can't remember what they were, like sharp, diffuse, principal. I think F was fundamental. So it's how they used to describe where they thought the electrons are, but again, they got rid of the word and they just kept the letter. All right. So let's go ahead and let's write the address of the electron in hydrogen. So if you look at hydrogen, hydrogen has 1 electron. So let's describe where that electron is. So on your periodic table, another thing I need to tell you is that there are rows. So we have rows 1 through 7. And these rows are the energy levels. Okay, so energy level. So it's not only the number of row, but it's also the energy level. So let's look at hydrogen. So hydrogen, it has one electron, and its one electron is in the S block, and it's in the first row. So I describe it as first row, S block, and then I need to tell how many electrons are in that S block. So I put a little 1. So this is the address of hydrogen's electron. So hydrogen is 1s1. All right, let's go to the next element. It's helium. Now helium, it really should be over here. So it is way over here, and that is because it's a noble gas. So they have placed it over there. But it really should be over there next to hydrogen. But let's look at helium. Helium has 2 electrons. So helium, with its 2 electrons, we need to describe its address. So first of all, the 2 electrons are in the same row, so number 1. It's an S block, and I need to say that I have 2 of them. So this is helium, 1s2. And I'm going to write it over here because that's where it really is, okay? But just know that they have taken it and they have cut it out and put it over there by the noble gases, because it is a noble gas. All right, I'm just going to get rid of this little line here so I have some extra room. All right, let's go to the next element. So the next element is lithium. It has 3 electrons. So it's going to have everything that came before it. So it's going to have the same electron from hydrogen and from helium, and it's going to have its own. So a total of 3 electrons. So I just take my finger and I read across what electrons it has. So it has this electron and this electron, so I would write that as 1s2. And then it's going to have its own electron right there in that space. So it's the second row now. It is still the S block, and I have 1 of them. So this would be the address of all the electrons of lithium. So let me just go ahead and add 2s1 right here. Okay, so I'm hoping you're starting to see maybe some patterns. Can you predict what beryllium is going to be? Beryllium has 4 electrons, so it has everything that came before. So it has hydrogen and heliums, so 1s2. It has lithiums, and it has its own, so 2s2. Now the little superscripted numbers, they should always add up to equal how many electrons you have. So with 4 electrons, we find that 2 are in the 1s2, and we find 2 in the 2s2. Okay, let's go ahead and go to boron. So boron has 5 electrons. So let's go ahead and write the address of all the electrons for boron. So we'll start with that hydrogen one and the helium, 1s2. And then we have the lithium and the beryllium, 2s2. And now, here's where boron is. And now we come to a new block. So what do we know? What row are we on? So we're on row 2, and we're in the P block, and we have 1 electron. So 2p1 is what boron is going to end in. Okay. Can you predict what the rest of those numbers and letters are going to be in the row? So following the pattern, I would expect that this would be 2p2, 2p3, 2p4, 2p5, and last in the row is 2p6. So this is the element neon right here. So let's go ahead and write neon's address for all its electrons. So it would be 1s2, 2s2, 2p, and I have all of them, so 6. Okay, so there's neon with 10 electrons. And you can see those 10 electrons because 6 plus 2 plus 2 equals 10. So what we've been talking about is something called an electron configuration. So an electron configuration, this is the address of where every electron is in the element. So you can kind of imagine when you get down to the bottom, how long are these going to be? So they're going to be pretty long. But let's go ahead and plug through and let's do some more. So I'm just going to clear up some room here so I have some room to write. So again, these are called electron configurations. So, and it tells exactly where every element or where every electron is in the element. All right, so let's come to the next element. So we're at sodium. So what do you predict that sodium's electron configuration would be? So we do have 11 electrons. So I'm just going to take my finger and I'm going to read the periodic table. So starting with hydrogen and helium, 1s2, 2s2, 2p6, it has all of those. And now we come to 3s1. So I'm now in the third energy level, or 3 levels away from the nucleus. So our atom is getting bigger. And can you predict what the element is going to end in next to it? You're right, 3s2. So I would know that I would continue the 3 p's all the way across. So following the pattern of 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Okay. All right, so let's come all the way to calcium right here. So calcium right here, we could quickly write its electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. So as you can see, it gets kind of long. There is an abbreviation, a way to write out the electron configuration without having to start at 1s2 or way back to hydrogen's electron. So what you do is they are called the abbreviated or the noble gas configuration. So what you're going to do is you're going to go back to the last noble gas. So if you follow calcium back, you end up at argon right here. So what you're going to do is you're going to put in parentheses, and they're like little block parentheses, the symbol for argon. And then you're going to say calcium has everything that argon has plus 4s2. So this is calcium all written out. And this right here is the abbreviated noble gas configuration is what it's called. Okay, so I went ahead and erased my work from before. Let's go ahead and continue on. So when we come here to the valley, something special happens. So the atom has grown quite large, so it's into the 4th energy level. And what it's going to do is it's going to go back to the 3rd energy level and stuff more electrons in the 3rd energy level. So it does this right here with scandium. So when you look at scandium, you should have 21 electrons. And reading the periodic table, you should have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And now, like I said, it's going to go back to the 3rd energy level and it's going to stuff more electrons in the 3rd energy level. So this actually is 3d1 is what it ends in. So this should be 3d1. So how I remember is that these are the 3Ds and there are 10 of them. So you would end with 3d10 over here. So, and I just remember 3D glasses. So it's just something you have to memorize. That very first row, it is going to be the 3Ds. So you go 4s1, 4s2, and then you're going to start counting the Ds off. So 3d1 all the way to 10. When you go to the P block, you will continue the pattern. We are still on the 4th row. So you just have to remember that that first row of your transition metals, those are your 3Ds. All right, here's my 5Ps, or excuse me, my 5Ss. And then right below the 3Ds, I would have the 4Ds. And then my 5Ps. Then I would have my 6Ss. And now right here, it does something special. Okay. So this is the start of our lanthanides. So it starts with lanthanum first, and they have kind of cut it a little bit funny. This is actually an F1 right here, and then you have an F2, an F3, etc., all the way to F14. And then you have to know that the F's start with energy level 4. So that's kind of weird. So my D's start with 3 right here, and my F's start with 4. So what happens is after energy level 6, it gets big enough that it's going to go back to the 4th energy level and stuff some more electrons in there. Okay, so these are your 4Fs. Can you predict what's going to be below the 4Fs? That's right, the 5Fs. And so you really have to pay attention to your numbers. So follow the numbers and let them guide you that you're going to go here, down to here. You'll go all the way across, and then you'll continue back with the 5Ds. Now, as I said before, they have cut it a little weird, and I actually messed up right there. The F14 is right there, and then this is a D1. So they just kind of cut it a little ski-wampus. That's why the periodic table in my room, I have little post-it notes that I label the D1. Okay, so this one's a D1 too. So this one would be the 5 D1, and this one would be the 6 D1. Okay, all right. So hopefully that's not too confusing. They kind of cut it a little bit weird. Let the numbers guide you. But this is basically how you do the electron configuration. So here is the periodic table that has not had the lanthanides and actinides cut out of it. And so just to illustrate what they did is they cut it right here, and then they cut into these D1s. And then they located this under your periodic table, and then they smushed it together. And that's just to make printing easier. So I wish they would just keep it like this because it makes more sense. But you can see that you can start here and you can read across and keep reading across and write those electron configurations. So one thing that I've seen students do is they try to separate and write all the P's. If you are all together, say you have neon, it would be a 2P6 at the end. Okay, so you wouldn't write 2P1, 2P2, 2P3. You would add them up all together. Okay, let's just do a couple of practice electron configurations. We'll just use this space here just to practice, and we'll do both the full electron configuration, and we will also do the abbreviated. Okay, so we really can do any element, so it doesn't really matter. Let's do like a really hard one just so that you can see how it works. Let's go ahead and do tungsten. And I say really hard, they're not really that bad. So tungsten has 74 electrons. So we're going to just start with our first element, so 1s, and it has both of those, so 1s2, 2s2, 2p6, 3s2, 3p6, so I'm just reading across. Then I drop and do my 4s2, and after 4s2, remember it stuffs in and goes to the 3ds. 3d10 has all of those, back to the 4s. So your s's and p's, you always just count by rows. So 4p6, then I have 5s2, and then I have my 4d10, I have all of those, and back to my p's, 5p6. Then we have our 6s2s. And remember, after your 6s2s, you're going to follow the numbering. So notice my periodic table, it'll go 56, 57, and 58 is going to be way down here. So you're going to have to follow that. And I have all of these. So I have all of these for Fs. So I'm going to say 4F14. Okay, then I follow my numbers all the way up, and I'm going to have 5D4. Okay, 1, 2, 3, 4. So this would be tungsten's electron configuration. If you add up the superscripts, you would find 74 electrons represented there. Let's write the abbreviation. So in the abbreviation way, you have to go back to the last noble gas. It has to be a noble gas, not any other gas, only noble gases. So follow your numbers, 74, 55, we're at 54. So this is going to be xenon. So this is saying tungsten has everything xenon has, and then you're going to write the extra. Plus 6s2, 4f14, and 5d4. Now, this is how we would predict the electron configuration to be. If you actually look up the electron configuration that is listed on the element, you're going to see some differences. So I'm expecting you to be able to write it exactly how I have written it, where you count each element. But just know that once you get to the energy levels of F's and D's, they're very, very close in energy levels, so sometimes they switch the electrons around a little bit. You're not expected to know that. You're expected just to be able to count the electrons using the periodic table and writing your electron configuration. So as I said before, the periodic table is arranged by protons but also electrons. And we find those electrons in, and we've talked about these, energy levels. So energy levels 1 through 7, or rows 1 through 7. And those blocks, S, P, D, and F, another name for them are sublevels. And this is just kind of summarizing up the electron configuration. When you look at each of the blocks or the sublevels, your S block can hold a maximum of 2 electrons because there's 2 columns. And the P sublevel can hold a maximum of 6 because there's 6 columns. The D, a maximum of 10 electrons. F, a maximum of 14 electrons. And this is by energy level. So if you had the 2s, you would have 2 electrons. If you had like the 5Ps, they would have 6 electrons. So that's what I mean by that. So as I said before, there are tons of exceptions in electron configurations. The general rule is, though, the electrons will always go to the lowest energy state. As you can see in this little orbital energy levels, you can see there's a lot of overlapping. And you can see energy levels where they're really, really close together. So it's easy for electrons to kind of move around a little bit, okay? There are 2 special exceptions that you should be able to know how to predict, and that is, one of them is copper. So if you look at copper, copper has everything that argon has plus 4s2, 3d9. So that's what you would predict. What you actually see is everything argon has plus 4s1, 3d10. So what's happening is that D sublevel, it's almost full. It has almost all 10. And so it will borrow an electron from the S sublevel. And this makes it a lower energy level and with greater stability. The other one that you should know is chromium. Again, you predict that it should be 4s2, 3d4, but what you actually see is that, again, it borrows an electron from the S sublevel. So we end up having a half-filled D sublevel, and just gives it a special stability.